So today we'll start a new unit that is about thermogravimetric analysis. Here we'll have an introduction to what is TGA, the instrumentation, the sources of error in TGA, how do we interpret the TG curve, the different factors which affect the TGA curve, and the applications of TGA in our analytical chemistry. So we'll first begin with a brief introduction to what is thermogravimetric analysis or TGA. So TGA is most widely used thermal method. It is one of the most widely used methods to understand the thermal stability of any material. So it is based on the measurement of mass loss of a material as a function of temperature. So we basically measure the amount of mass that is lost from our material as we keep on increasing the temperature. So in thermogravimetry, a continuous graph of mass change against temperature is obtained when a substance is heated at a uniform rate or at a constant temperature. So this process is also called as we use the term thermogravimetry, which means that upon heating the loss in the mass. So with respect to temperature, so that then the plot that we curve is the temperature is taken in the x-axis and the mass loss that is taken in the y-axis. So and what important factor here is that the temperature that we keep on increasing, it is maintained at a uniform heating rate. So and then the mass loss versus the temperature plots, it gives us the TG curve, or we call it as the thermogravimetric curve. So a plot of mass change versus temperature is referred to as the thermogravimetric curve, or we call it as the TG curve. So from the TG curve, we generally plot the mass that keeps on decreasing along the y-axis, and the temperature is taken in the x-axis. So here is a typical diagram of a TG curve that has been shown here in figure 10.1. So sometimes if the temperature, we may plot time t. Sometimes time t is taken and in place of temperature, and that also gives rise to a different decomposition temperature. So here we'll gradually see what are the different types of TG curve and how do we interpret the TG curve. So first we'll start with the instrumentation. The instrumentation of a here TG curves, here it talks about the different types of what is the basic composition of the instrument that we use in a TG curve. So first is the instrument that we used in thermogravimetry, we call it as a thermobalance. So this thermobalance, it consists of several basic parts. So what are the basic parts? The basic components of a typical thermobalance, it consists of a balance, a furnace that is used for heating. Then we have a programmer, that is the unit for temperature, for maintaining the temperature, and the recorder which the recorder, it records the changes in mass loss with respect to temperature. So here in figure 10.2, you can see this is the block diagram of a thermobalance that it has been shown here. So and how the arrangement is made inside the instrument of the TG. So what is this balance? So the basic requirement of automatic recording balance, it includes accuracy, sensitivity, reproducibility, and capacity. So here the balance that is used in TG, it must be very sensitive and accurate. So recording balances, they are basically of two types. One we call it as the null point, and the other is called as the deflection type. So this null type balance, it is more used because it detects a deviation of the balance beam from its null position. So it is very sensitive. Deflection balance of the beam type, it involves the conversion of the balance beam deflection about the fulcrum into suitable mass trace by photographic reading. So mostly when we talk of TG, we use the null type balance. Then comes the furnace which is used for heating our sample. So this furnace and control system, they must be designed to produce linear heating. So that is, it is designed in such a way that the heating that is done in this TG, it should be maintained, it should be linear, and there should be no deviation in the heat scanning rate of the of the heating that is during the process. So avoid temperature range that is from 150 degree to 2000 degrees furnaces is mostly used for this. They are we know that this up to 2000 degree temperatures, that is also furnaces are used, because normally TGV people for solid state chemistry or for very heat resistant materials, people need to measure the thermal stability of the material up to 2000 degrees centigrade. So basically, the furnaces have also been designed that can sustain temperatures up to 2000 degrees centigrade. Then the temperature measurement and control. So these are done, the temperature measurements are usually done by instruments, they are called as thermocouple. So the thermocouples like chromal aluminum thermocouple, they are used because they can go up to a temperature of 1100 degrees centigrade. Whereas if we have a platinum and 10% rhodium thermocouple, then they can go up to a temperature of 1700 degrees, 1750 degrees centigrade. So depending on our temperature requirement, we can install the thermocouple to get the required temperature. Then comes the recorder. So the graphical recorders, they are preferred to meter type recorders. So the XY recorders, they are commonly used because they plot weight directly against the temperature. The present instrument, they facilitate microprocessor controlled operation and digital data acquisition and better processing unit, because here when we, this is the figure 10.3, you can see the schematic diagram of a typical balance and furnace assembly. So here, when we work with a modern day TG instrument, we directly put our sample with the proper scanning rate, which directly gives us the digitalized data. So, but the in today's the modern TG instrument, the balance is highly sensitized. The thermocouples, they maintain to the control the exact temperature, and we get the data just in a digital output. So thermogravimetric curves. So thermogravimetric curves, as we have talked, that it depends. It is the plotted the mass loss versus the temperature or time. But mostly we plot it as the in x-axis. It is the temperature, and here is the mass loss. So, but in some cases, we can also plot the derivative of the mass loss. That is the first derivative of the mass loss. It can be plotted, and then we can, this is called as a DTG plot, that is the derivative thermogravimetric curves. So what does this DTG curve represents? It is the first derivative of curve of the mass loss versus the temperature or time, that is here taken in the y-axis. So here in figure 10.4, the bold line, it represents the TGA curve, and here the dotted line in this figure, it represents the DTG curve. Then coming to what are the sources, probable sources of error in TGA. So as we know, this instrument, it is highly sophisticated instrument, and the possibility of any error arising in TG measurement is very low, because we use sophisticated balances, and as the temperature scanning rate is uniform, so we expect that the errors, the errors will be very less. But in actual practice, there are different sources of errors that can arise in TGA. So because we know if there is any error, then our data will be misinterpreted. So we should also take care of certain precautions while we working with TG. And some of the common errors that arise while working with TG is, first is the Buance effect. So what is this Buance effect? So if we take a thermally inert crucible, so when we take our sample in TG, we take aluminium pans, and then we directly weigh a very small amount of our sample, and then the TG experiment is measured. But if we take a very thermally inert crucible, we know that the TG scanning, it can ranges from room temperature to 1000 or 2000 degrees centigrade. So if our crucible is not stable up to that temperature, then we can see there is an apparent weight change arising due from the crucible, and also arising due to the mass loss of the sample. So here this is called as Buance effect. So what we do to avoid this Buance effect, it is always necessary that we run the blank run without the sample, only the empty crucible, so that we can know how much error is present due to the heating of the crucible. Then the second source of error that comes is from the condensation on the balance suspension. Now, if our sample it has the tendency to undergo condensation, then this will also affect the mass of the sample. And if the mass of the sample is, if it arises or if it goes down during the measurement of the TG, then we see that the TG curve, the shape of the TG curve will also be disturbed. So this can be avoided by maintaining a dynamic atmosphere around the sample in the furnace, so that all the condensable product that is present in our sample may be driven away by the gases. Then comes the random fluctuation of balance mechanism. If there is any reaction between the sample and container, we also see an error. If there is a convection effect from the furnace, then error also arises. If there is a turbulence effect from gas flow, that is in TG, the it is always carried out in nitrogen atmosphere. So now, if due to certain due to certain imbalance, if we see a turbulence due to the nitrogen, then error also arises during the measurement. Also, if there is an induction effect from the furnace, then the TG curve is also affected. So here the errors of type 3, that is the random fluctuation of balance, can be avoided by proper placing of the balance in the laboratory. And the error 5, that is the convection effect, it can be avoided by proper choice of the sample container. Now, the last three errors, they have to be considered during the design of the furnace. So, by avoiding excessive heating and proper gas flow, some of the above errors they can be avoided. But invariably, while we are working with TG, more or less some errors also arise due to human handling. So, in light of above discussion, it is also necessary to calibrate the thermobalance before use. So, calibration of the thermobalance is for the measurement of the mass. Now, how can it be done? It can be done by adding a known mass of the sample container and noting the reading in the chart. So, the temperature calibration can also be done by using ferromagnetic standards. So, first, whenever we start doing our TGA, it is always advisable that we calibrate the thermobalance and we calibrate our temperature. So, with this one process of calibration is sufficient enough to lower down many human errors that might arise during the handling of the TG instrument. So now coming to the interpretation of the curves. So how we can interpret TG curves. Now we know that TG curves, they are just simple plots where the temperature is taken in the x-axis and the mass loss of the substance is taken in the y-axis. So here, using this TG curve, we can talk about the thermal stability of the material. We can also relate the mass changes to the stoichiometry of the substance. So this can often lead us to the direct quantitative analysis of the sample whose quantitative composition is known. So now let us take an example of the TGA curve of calcium carbonate. So here in figure 10.5, you can see this is the both the TGA and DTG curve of calcium carbonate at various heating rates. So what happens is, TG means the x-axis is the temperature, y-axis is the mass loss, and DTG curve means the x-axis is the temperature and y-axis is the mass, the first derivative of the mass loss. So here, in case of A, B is 10 heating at 10 degrees centigrades per minute and C is heating at 3 degrees centigrades per minute. So here you can see this is the TG and DTG curve. Now these curves indicate that calcium carbonate decomposes in a single step between 800 degrees centigrade and 950 degrees centigrade. Here, if we look into this curve, we see between 850 degrees centigrade and 950 degrees centigrade, calcium carbonate, it breaks down to form calcium oxide and carbon dioxide. So here we know this is the chemical reaction that involves the breakdown of CaCO3 to calcium oxide to to carbon dioxide. So here if we look into figure 10.5c, so in 10.5c, it indicates the percentage of mass lost by the sample is between 800 and 950 degree. So if you look into figure C, here it is given in dotted lines, and between 850 to 950 degrees centigrade, if we look, then the percentage mass loss is given by 44. So now this exactly corresponds to the mass change calculations based on stoichiometry of the decomposition of the calcium carbonate. Here it is shown in equation 10.1. So then by the percentage weight loss, here it can be calculated as 44%. So now we have also seen how TG curves is related to. Now here from this example we can see how TG curves is related to stoichiometry. Now in this second example we will see how it can be used to compare the thermal stability of different materials. So such information is very required because if we have a series of compounds and we want to study their thermal stability, then TGA is a very good instrument because it will not only tell us about the decomposition temperature, but it will also give us the thermal stability of the different materials that we have taken. So how is this done? So here an example is given in figure 10.6. So this figure 10.6, you can see this is the TG curves of some very common polymers. PVC is polyvinyl chloride, PMMA is polymethyl methacrylate, LDP is low density polyethylene, PTFE is polytetrafluoroethylene, and PS is polystyrene. So you see each curves, they have the each polymer, it has a different, or the nature of TG curve is different for different polymers. So here 10 mg all samples has been taken, the heating rate has been maintained at 5 degrees centigrade per minute, and the temperature is maintained as nitrogen temperature. So now we will analyze this curve. Now here we see the decomposition temperature. If we look into for PVC, that is polyvinyl chloride, it is the lowest and almost corresponding to that of 200 degrees centigrade. So then if we look into PMMA, it slightly increases and probably we can say that it goes to 300 degrees centigrade. So similarly again for LDP, that is low density polyethylene, it increases to about 450 degrees centigrade. Then overall if we look into polystyrene, then the decomposition temperature, it goes well beyond 550 degrees centigrade here at this point. And this shows that among all the polymers, the PS, that is the polystyrene, is the most stable polymer among all, with around stability almost going to around 600 degrees centigrade. So this is how we compare the thermal stability of different polymers. So now coming to the factors influencing the TG curve. So TG curve, as we see that it is the TG curve we plot as the mass versus temperature curve. So we know there are various factors which will definitely influence the TG curve, and some of first we will talk about the instrumental factors. The first instrumental factor is the furnace heating, the recording speed, the furnace atmosphere, the geometry of the sample holder, the sensitive recording mechanism, and the composition of the sample container. Then the sample characteristics will also affect the TG curve, like the amount of sample that we have taken, the solubility of the gases that is evolved from the sample during the measurement, the particle size, the heat of the reaction, the nature of packing inside the sample, the nature of the sample, and the thermal conductivity of the sample. So we see that both instrumental factors and sample factors, they both contribute to the nature of the TG curve. So we'll first look into these factors into some in details. So first is the furnace heating rate. So we know that at a given temperature, the degree of decomposition is greater, the slower is the heating rate, and thus it follows that the shape of TG curve can be influenced by heating rate. So we have seen that the TF is greater than TS, the T final is greater than for the T final, and here F indicates the fast and slow heating rate respectively. Like to understand this, let us take an example. So calcium carbonate, it not would not show any mass loss below 600 degrees centigrade when it is heated in a thermos balance heating at a rate of 3 degrees centigrade per minute. But we know that carbon dioxide is evolved at 250 degrees centigrade. So this is how it works. So similarly, polystyrene, it decomposes only by 10% when heating rate is 1 degree centigrade per minute, and it decomposes 10% by mass when heating rate is 5 degrees centigrade per minute. So it has been observed that both the final procedural temperature, it will decrease with decreasing in heating rate, and TG curve will be shifted towards the left. Then coming to how the chart speed affect the TG curve. The chart speed on the recording of the TG curve, it of rapid or slow reaction has much effect on the shape of the TG curves. Now, if we take a slow decomposition reaction, then the low chart speed is recommended for the TG curve. For a slow reaction followed by a rapid one at the lower chart speed, the speed curve will show less separation. For a very fast reaction followed by slower, one similar observation was observed in shorter curve plateaus. So then coming to the furnace temperature. So the effect of atmosphere on the TG curves depends on the types of the reaction, the nature of the decomposition products, and type of the atmosphere that is employed. Mostly, in all of the cases, TG is carried out in nitrogen atmosphere, but depending on the nature of the sample, sometimes dry oxygen atmosphere is also taken. So here in figure 10.7, the TG curve of calcium oxalate in dry O2 and dry NO2 has been shown here. So if we look carefully, here in N2 atmosphere has been represented in bold lines, and O2 atmosphere has been represented in dotted lines. So the first step, if we look here, there are various stages of decomposition of calcium oxalate. So here the first step is the dehydration process, that is calcium oxalate, it for the moisture is first removed in the form of H2. Then if you see from 100 to 200 degrees centigrade, both the curves, they go in the similar way and there is no change. In the second step, the calcium oxalate, that is here, it breaks to form calcium carbonate plus CO. So the curve here you can see at 400 degrees centigrade for the oxygen atmosphere, here it diverges, because what happens here is the curve diverges in O2 atmosphere, because the oxygen, it reacts with the CO that is evolved here, it now reacts with the oxygen atmosphere, and it to form the second oxidation reaction. However, the CO that is evolved in nitrogen atmosphere remains as such, it doesn't react in that with nitrogen. Then the third step is the decomposition reaction, is also, it is a reversible reaction, that is the calcium carbonate here that is formed in the second step, it now breaks into calcium oxide plus carbon dioxide. Now this step, it should not be influenced by O2 or N2, because this step isn't, because neither CaO nor CO2, they react with the oxygen atmosphere or the nitrogen atmosphere. So however, still, if we look into this point 700 to 900 degrees centigrade, we see that the oxygen curve is a bit higher than that of the nitrogen curve, but this difference is very small and it can be neglected. But why does this difference arise? Now, because of the rate of the decomposition of calcium carbonate in these two atmospheres, but this the difference is not much. So you can see how the nature of the atmosphere, furnace atmosphere, that is the nature of the gas that we are taking while performing TG experiments, also affects the TG curve. Then comes the effect of sample holder on the TG curves. Now the sample holders, they range from flat plates to deep crucible of various capacities. The shape of the TG curve will vary as the sample will not be heated in identical conditions. So generally it is preconditioning that the thermocouple is placed near the sample as possible, and it is not dipped into the sample because it might be spoiled due to sticking of the sample to the thermocouple. So thus it leads to source error. So if the sensitivity of the recording mechanism is not enough to record the mass change, then it will also cause a error in the measurement. So it is always advisable that we will take a sample holder in such a way which will not react with our sample, plus it will also be very sensitive to the minute mass changes that occur during the TG experiments. Then coming to the effect of sample mass. The sample mass, it affects the TG curves in the following way. We know that while performing TG experiments, we need to take the mass of the sample, a minimum 5 to 8 mg of the sample it is required. So even with this much low mass, the sample mass will also affect the TG curves. So how does it affect the TG curves? The endothermic and exothermic reactions of the sample, it will cause the sample temperature to deviate from a linear temperature change. So if we have, if the nature of our sample is such that it is like it has the property of endothermic or any exothermic nature, so then there will be a mass change which will affect the, ultimately it will affect the TG curve. The degree of diffusion of the evolved gases through the void space around the solid particles will also affect the nature of the TG curve. The existence of large thermal gradients through the sample. Now, if our sample it has a low thermal conductivity, then definitely the nature of the TG curve will be hampered, because overall the TG it measures the mass loss versus the temperature. So as it is, if our sample is has low thermal conductivity, so the TG will also be, curve will also be affected. So therefore it is always preferable to use a small sample as possible, depending on the sensitivity of the valence. So that is why we always measure TG samples, mostly like 5 to 8 mg or maximum 10 mg of the sample they are taken. So then coming to effect of sample particle size. The particle size will cause a change in the diffusion of the evolved gases, which will alter the reaction rate and ultimately the shape of the curve. The smaller the particle size, then greater is the extent of decomposition at any given temperature. So the use of large crystal may result in apparent rapid loss mass during the heating. So this is also due to the mechanical loss of the sample by forcible ejection from the sample container, where the gases that are evolved during the measurement also they accumulate and suddenly they are released. So the sample particle size will also decide the nature of the TG curve. Then coming to the effect of the heat of reaction. Now this heat of reaction, that is delta H, it will also affect the TG curve. Suppose the we have a temp, because this TG is highly dependent on the temperature, then if our sample is endothermic or exothermic nature, then our TG curve will be affected. The other sample characteristics such as sample packing, nature of the sample, thermal conductivity will also affect the shape of the TG curves. If the sample is packed very loosely, then the gas will diffuse out more easily. But if the sample is packed very tightly, then the gases cannot evolve properly, so they will need more force. So as a result, this will also affect the TG curve. So if the sample reacts with the sample container on heating, then it will not give the mass of the product, then it will not give the mass of the product form, so the sample will change. So we can also, these effects they can be avoided by taking proper container for our sample. So now coming to applications of TGA. So why TGA is important and why do we need to study TGA? How TGA is helpful in analytical chemistry. So first is some important applications of TGA. They lie in knowing the purity and thermal stability of substances. They are used in solid state reactions. You are used to study the decomposition of various organic and inorganic compounds. They're used to study the determining the composition of mixture in corrosion of materials in metals in various atmospheres, the pyrolysis of coal, petroleum, and wood, reaction kinetics, roasting and calcination of temperatures of minerals, evaluation of gravimetric precipitates, the oxidative and reductive stability, the determining the moisture, volatile, and ash contents, and they are also used to know desolvation, sublimation, polarization, vaporization, desorption, and chemisorption reactions. Now here we'll study one by one how they are useful in analysis of different types of organic and inorganic mixtures. Now first let us consider a binary mixture. So here a binary mixture, it consists of two compounds, that is AB and CD, which has characteristic TG curves. Here it has been shown. If we look into figure 10.8a, this is the TG curve. The first represents the TG for the AB compound, and second represents the TG curve for the CD compound. So first we will analyze that of the AB and CD curve. So the decomposition of the, that is AB and CD, they are the pure compounds. So here first they occur at the temperature. Here if the, for this AB compound, the first decomposition temperature, it occurs at the temperature T1, and the second decomposition, it occurs at temperature T2. So here for this the T1, it for AB, it occurs as this point, and the T2, it occurs for this point. So here it has been labeled as BC and FD. So here BC and uh, BC and FG. Here it has been shown. So the TG curve of the mixture of AB and CD of this compound, it is now here, it is shown in figure 10.8. Now if we look into the mixture of AB plus CD, we can see that the plateaus, they also form about the same temperature as they do in the TGO curves of the pure compounds. Now here, by measuring by all these quantities, the X value from X value and Y value, and comparing with the parent, we can understand how they determine the quantity of AB and CD. So here one example has been given for calcium and magnesium carbonate. How we will know the amount of calcium carbonate and magnesium carbonate that is present in the mixture? So this figure 10.9, this is a mixture for this is a TG curve for the mixture of calcium and magnesium carbonate. So here we see this before 210 degrees centigrade, some mass loss has been done. So significant here, it was 100%, and here mass loss has been done. So a significant amount of mass has been lost. Now this is due to the first is the anything that is heated beyond 100 degree up to 150 degree, here it is due to the amount of moisture, and that is lost from the sample. Then another mass loss, here we can see the second mass loss, it occurs at around 400 degrees centigrade, 480. So 480, why does this, what happens here is the magnesium carbonate, it breaks down to form MgO plus CO2. Now here in the third step, that is between 600 degrees centigrade and 900 degrees centigrade, the calcium carbonate that is present, it decomposes to form calcium carbonate, calcium oxide plus carbon dioxide. Now here the portion of the curve, that is AB, it represents, so at this point we have two possibilities, that is the mixture of MgO and CaO. Now here we know the value, the plateau here, it corresponds to M1, and for CD, here the plateau here, it corresponds to CD, and we can write it as M2. So both these plateaus AB and CD, they represent M1 and M2. So here now we see M1 is due to CaCO3 plus MgO. So thus M1 minus M2, it will give us the loss of carbon dioxide, due to the breaking of the calcium carbonate. Then particular using all the value M3, that is the mass of calcium oxide, it can be calculated, and using this equation we can finally calculated the mass of the using the molar values, we can calculate, this has all been done here, and then we can calculate the amount of Mg that is present in the original sample. So this is how TG curves can be used to determine the amount of a particular metal or organic or inorganic material that is present in the sample. Then we will analyze the mixture of calcium and magnesium oxalate. The here the DTG and TG curve for calcium oxalate has been shown in figure 10.10. So calcium oxalate, it is monohydrate is unsatisfactory form of determining calcium oxalate, because it tendency to remain excess to retain excess moisture even at 110 degrees centigrade. Anhydrous calcium oxalate is hygroscopic, but Calcium carbonate is excellent weighing form if heated to 500 degrees centigrade. So above 635 degrees centigrade, the decomposition of calcium carbonate starts to become significant under usual laboratory conditions and completely converted to calcium oxide at 900 degrees centigrade. Thus, calcium oxide monohydrate decomposes in three steps. So first, dehydration, second, removal of CO and formation of CuCO3, and third step is the decomposition of CaCO3. So here the three steps are given. Calcium oxalate, first it loses water at about 135 to 200 degrees centigrade. Then the calcium oxalate that is formed, dry calcium oxalate, it decomposes to form calcium carbonate plus CO at about 400 to 480 degrees centigrade. Then beyond 635 degrees centigrade, the calcium carbonate that is formed, it decomposes to form calcium oxide plus carbon dioxide. But in case of magnesium oxalate, dihydrate, it directly decomposes. Here the decomposition, it takes place in two steps. Here the in magnesium oxalate dot 2H2O, the two molecules of water, they are directly removed at about 135 to 200 degrees centigrade. And in the second step, this magnesium oxalate, it breaks down simultaneously in two steps. It breaks down to magnesium carbonate, then subsequently it is beyond 500 degrees centigrade, it is unstable in nature, and it immediately forms MgO plus CO2 above 500 degrees centigrade. So this is how the curve it looks like. The TG curve for the mixture, it shows two mass loss up to, if you look into beyond 500 degrees centigrade, it shows two mass loss regions. The first is about 200 degrees centigrade, where there is mass loss due to loss of moisture. Then we have a mass loss in the range of 390 to 500 degrees centigrade, that is due to decomposition of both magnesium oxalate and calcium oxalate. Beyond 500 degrees centigrade, that is only due to the calcium carbonate, because beyond 500 degrees centigrade, the magnesium carbonate has already been broken down to MgO. So here M1 M2 are the masses of the mixture taken. If we know the value exactly, then we can calculate the amount of calcium and magnesium that is present in the original sample. So this is how TG curves are used in analyzing or in knowing the exact amount of the materials that are present in the sample. So here is a third example of a mixture of silver nitrate and copper nitrate. The TG curve of pure silver nitrate, copper nitrate and their mixture, it has been shown in figure 10.11. So if you look here, the first one is for silver nitrate, second is for copper nitrate, and the third is for the mixture. Now we will look into this figure carefully. So we know curve A. Here up to for the curve A, that is for silver nitrate, there has been no decomposition, and the first decomposition temperature, it occurs at around 473 degrees centigrade, followed by the next which comes at around 608 degrees centigrade. So here after this 608 degrees centigrade, the mass loss is very slow. So here what happens is, in the first step, the silver nitrate, it decomposes to AgNO2 plus O2. Now this decomposition of AgNO2, again it occurs to form Ag plus NO2, and beyond 800 degrees centigrade, there is the weight gain remains constant, because the pure Ag metal is present and there is no change in the mass of the Ag that was formed during the reaction. Now here we will look into the copper nitrate reaction, if the TG curve. So here we see there are three temperatures that has been marked for this reaction: 151, 200 and 278. So where does these three temperatures occur? The first is up to, if you look here, up to 100 degrees centigrade, there is no mass loss. Beyond that, after 100 degrees centigrade, that is due to the 150 to 200 degrees centigrade, it is due to the a horizontal line it appears, and here it has been shown that it forms basic copper nitrate, that is CuNO3 whole 2 dot 2 copper hydroxide. Beyond 200 degrees centigrade and up to 610 degrees centigrade, the compound it decomposes very slowly, vigorously, and we see it forms CuO, which becomes constant up to 900 degrees centigrade. So here we can write that copper nitrate dot 6 water, that is hexahydrate. First, it forms a copper nitrate dot 2 copper hydroxide, which is basic copper nitrate, which then decomposes to form CuO. Now, if we place the mixture of silver nitrate and copper nitrate in a balance, then we see the curve C. It shows the nature of the curve C. It is like this. So the horizontal is related to the basic copper nitrate, and it can be looked from 240 to plus copper. Above 900 degrees centigrade, we have only silver plus copper oxide that is present here. So here, looking at the, then comparing the masses, we can actually know the original mass of the elements that are present in the mixture. So then we will talk about a complex mixture. How does we know the amount of the mass that is present in the complex mixture? So for a complex mixture, so we'll take a mixture of calcium, strontium and barium oxalate, and it is noticed that in between 100 and 250 degrees centigrade, there is moisture loss from the sample. The moisture loss means that is the loss of water of hydration, and a horizontal weight level from 250 to 360 degrees centigrade is noted, which is also corresponds to the composition of the anhydrous metal sulfates. So this is the, in figure 10.12, this is the TGA curve of the mixture of calcium, strontium and barium oxalate. You can see then all the three oxalates, they decompose simultaneously to the carbonates, and the process is completed at 500 degrees centigrade. So if you here, they are all converted to their carbonates at 500 degree centigrade. Then from 500 to 620 degrees centigrade, here the anhydrous carbonates, they are stable in nature. If we heat them beyond 620 degrees centigrade, then the it follows to form their oxide by the decomposition of strontium carbonate from 860 degrees centigrade to 1100 degrees centigrade. Barium carbonate begin to decompose. So here, this is how we will relate all the three temperatures to the different mixtures. So first is the mass of hydrated oxalates, that is M of S. Loss of water M1, mass of CO formed, that is M2, mass of CO2 formed, that is formed by the decomposition of carbonate M3, and by followed by the decomposition of strontium carbonate, it is M4. Then knowing all the masses, we can calculate the, from the amount of the mixture that we have taken, and knowing all the masses, we can calculate the exact amount of the substance that is present in the mixture. Now these are all the analysis of inorganic mixtures. Now how is TGA helpful in the analysis of organic mixtures? So TGA has also been used in the determination of amount of vinyl acetate in copolymers of vinyl acetate and polyethylene. So if we take a mixture of vinyl acetate and polyethylene, then TGA can be useful to know the amount of vinyl acetate that is present here. So when vinyl acetate is heated, it loses acetic acid at about 340 degrees centigrade. So the temperature curve for vinyl acetate copolymers, here it has been shown in 10.13. So the TG curve shown in figure 10.13 for vinyl acetate polyethylene copolymers, they indicate the loss of acetic acid at about 340 degree here, for 340 degrees centigrade, due to the decomposition of vinyl acetate. Now each molecule of vinyl acetate, it loses 1 mole of acetic acid. So the amount of vinyl acetate in the polymers can be calculated accordingly. So we have that here in this curve, you can see 100 mg of the sample is taken in N2 atmosphere, and the scanning rate is maintained at 5 degrees centigrade per minute. So the vinyl acetate is equal to the mass of the acetic acid into molar mass of vinyl acetate by molar mass of acetic acid. So the percentage here, it can be shown here as this is 100, and beyond this is up to 390, that is your 23%. So here we get the Va percentage decomposition, the amount of vinyl acetate that is present, it has been calculated to be 33%. So this is how we can calculate the amount of the, we can analyze a organic mixtures. Now, gravimetric precipitates, they should be either dried or ignited. So, what does this mean? So, this means that uh, whenever we are performing any TG experiments, it should be noted that the material, they should be correctly dried properly for or the determination of application. First we will here we will see another important application of TG is the determination of correct drying temperature for precipitates in gravimetry analysis. So, for example, so let us take here, and we'll take a very common example. Uh, so suppose take silver chloride is dried at 130 to 150 degrees centigrade, and barium sulfate is heated to 800 to 900 degrees centigrade. So here we will make use of our TG curves. It is assumed that the horizontal portion of the TG curve, it gives the range of temperature over which the composition is constant, and therefore the mass is also constant. The precipitate, it can be dried in this temperature range for gravimetric analysis. It has been reported that the precipitate of aluminum hydroxide should be ignited at 1200 to 1300 degrees centigrade to form aluminium oxide. But with the help of TG curve, we have known that the precipitate may be ignited at 1030 degrees centigrade in order to get the aluminium oxide. So TG curve distinctly tells us the exact temperature at which the precipitate should be dried. So in TG curves, the distinction of the crystal, that is the elimination of water and ammonia at 30 degree, is done so that there is no possibility of weighing anhydrous beryllium phosphate. So here we'll also talk about the analysis of polymeric materials. The thermogravimetric analysis, it has actually very important application in polymeric analysis, because it talks about the different, apart from thermal stability, it talks about the different mechanism by which a polymer degrades. So the main conclusion drawn by TG are the thermal stability, compositional analysis, lifetime assessment, and degradation kinetics. So here from TGA curves, different, the route by which a polymer degrades can be categorized. Like first is by main chain scission, side chain scission, elimination, depolymerization, cyclization, and cross-linking. So TG curves not only talks about the thermal stability of the polymers, it also talks about how the polymer, it degrades, leading to its internal mechanism. So here only the steps 1 to 4, here these four steps 1 to 4, they can be detected in TGA. So here in figure 10.6 we have shown the TG curves of different types of polymers, and then we also talked about how the different onset of degradation temperature, so this can also predict the stability of the polymers. Then the importance of TG in reaction kinetics. So TGA has also been used to elucidate the kinetics of decomposition reactions. So this involves analyzing the shape of the TG curve. So in general, the rate of the reaction at any measured temperature is proportional to the slope of the curve. But a number of uncertainties sometimes make this analysis of questionable value. So the temperature dependence of any chemical process is described by the Arrhenius equation, that is K is equal to A into E to the power minus EA by RT. We know this. This is the general relation, that is for d alpha by dt is equal to K alpha to the power m into 1 minus alpha, where alpha represents the fraction of the reactant that has decomposed. So using this equation, we can find out how the kinetic analysis. So this is table 10.2, some of the rate equations that is used in kinetic analysis, and with this we can predict the nature of the reaction kinetics using TG. So this is all about TG, the instrumentation, and here we'll just take a break of 10 minutes and starts with DTG, DSC, and thermogravimetric titrations. So now we'll talk of DTG, DSC, and thermometric titrations. So first is, what is DTG? So DTA, differential thermal analysis. So differential thermal analysis, it is most widely and very suitable technique for estimation of in analytical chemistry. So here this is a DTA curve, that is mass loss. These are not this is versus temperature. Here change in temperature versus temperature, and here this is a DSC curve. This is the enthalpy change, the and versus the temperature. So first is the principle of DTA. So differential thermal analysis is a technique in which the temperature of the substance uh, is compared with the temperature of a thermally inert material such as alpha aluminium, and is recorded with furnace temperature as the substance is heated or cooled. So the range of temperature measurable in the course of DTA is much larger. Thus, during TG, pure fusion reactions, crystalline transition, TG, and crystallization solid states with no volatile product could not be indicated. But these changes, they are captured by DTA. So since DTA is a dynamic method, it is essential that all aspects of the technique be standardized in order to obtain reproducible results. So these include pretreatment of specimen, particle size and packing specimen, dilution of the specimen, and nature of the inert dilute. So the principle of method, it consists in measuring the change in temperature associated with the physical or chemical changes during the gradual heating of the substance. The thermal changes due to fusion, crystalline structure inversions, boiling, dissociation, oxidation reduction reactions, these are all accompanied by a rise or fall in temperature. Thus, they are all measured in DTA. So generally, to say that the phase transitions and other dehydration, reduction, and decomposition reaction, they produce endothermic effects, whereas crystallization, oxidation, and decomposition reaction, they produced exothermic effects. So in DTA, a sample under investigation, it is placed in a thermal inert material, that is mostly calcite or alpha alumina, in the sample holder. The temperature difference between the two is recorded as they are heated. So characteristics of DTA curves: when we plot a DTA curve, the temperature is taken in the x-axis, and the change in temperature, that is delta T, it is measure taken in the y-axis. So endotherms are plotted. If we have a downward peak, then it is called as an endotherm, and if we have an upward peak, it is called as an exotherm. So here, the when no reaction occurs in the sample material, then the temperature of the sample is equal to the temperature of the reference. So this is because both are being heated under an identical temperature. So delta T, that is between Ts minus Tr, that is the sample temperature, and reference temperature, is 0. So but as soon as the reaction starts, the sample, it either becomes hot or cold, depending upon whether the reaction is exothermic or endothermic nature. So a peak, it develops. If it goes upwards, then we say it is exothermic, and if the peak goes downwards, then we can say it is endothermic. Now here, if we look into figure 11.3, we see that the point C, the at the maxima, it gives the exothermic peak, and the point F at the minima, it gives the endothermic peak. So, in mostly when we look into DTA experiments, the exothermic peaks do not are of much important. We always look into the endothermic peaks. So, at some determinant point, the heat of evaluation process is completed, and after this, the heat evaluation goes up to temperature D. So, here up to temperature D is recorded, and the usefulness, it arises of this method. It arises due to the fact that the temperature peak is normally characteristic of the materials. So area of the peak BCD, it is proportional to the amount of reacting material. For endothermic reaction, the peak EFG will be obtained as it is shown in the idealized curve. So here we will use negative sign for endothermic reaction, that is when delta H is greater than 0, and we will use delta H negative sign when delta H is less than 0. So K is the here peak area, can be calculated as delta H into M into K. K is called as the calibration constant, which is temperature dependent, and it is determined during DTA calibration. So once we know the value of the calibration constant at a particular temperature, then the peak area can be used for quantitative analysis to determine the mass of sample or energy. So besides this DTA curve, it is also helps in estimating the heat capacity of the sample. So how it is helpful? So DTA curve, from DTA curve, the heat capacity, that is delta Cp, it can be measured as 1 by m by heating rate, or we can write it as d by dt of d by dt into 1 by m. So now coming to the instrumentation of a DT. So here in figure 11.4, you can see the block diagram of a DTA. That DTA, it here it is has been shown a schematic diagram of DTA. So it consists of following basic components, that is furnace assembly, sample and reference holder, temperature programmer, amplifier and recorder, and the atmosphere control equipment. So the instrument, it measures the differential temperature of the sample as a function of temperature. So source of uniform heating, nichrome furnace can be used up for measuring for temperature up to 1300 degrees centigrade. Platinum and alloys, it measures up to 1750 degrees centigrade, and molybdenum is used for higher ranges up to 2000 degrees centigrade. So depending upon our temperature, the heating source can be used. Temperature regulating system. So uniform rate of the heating is ensured through electronic temperature regulators. Specimen holder, it is designed to accommodate even a very small quantity and to give maximum effect. So the sample holder can be made up of platinum, nickel, stainless steel, Ag and alloys such as platinum, rhodium. Certain ceramic materials such as sintered alumina, silica, fire clay, heat resistant glass, and even graphite has been recommended as material specimen holders, but mostly alpha alumina is preferred. So measurement of temperature, rare metal alloys such as platinum, rhodium alloys, they are used as thermocouple for measuring the temperature. When we need temperature for more than 2000 degrees centigrade, then tungsten molybdenum thermocouple is used. So for temperature recording system, visual galvanometric observations are have also been used. Nowadays we have automatic pen and ink electronic recorders. Then direct recording of the heating curve. When a sample is heated at a constant heating rate, the slope of the heating of the curve, it remains constant. So at the moment when an exothermic or endothermic reaction takes place, then the slope of the curve, it changes. So exothermic reaction, it causes upward slope, and endothermic reaction, it causes a decrease in the heating rate. So these changes, they are detected by the detectors. These detector thermocouples, they are present, and they are also very sensitive to measure the minute changes in the temperature. Then what are the various factors that affect the DTA curves? So DTA curves are also influenced by basically two type of factors. One is the sample factors, similar to that of TG, and second is the instrumental factors. The instrumental factors, they include shape and size of the sample holder, the sample holder material, heating rate of the sample, sensitivity of recording system, the location of the thermocouple, and all such. Then the sample characteristics are also they also influence the DTA curve, like the amount of sample, particle size, packing density, heat capacity, thermal conductivity, degree of crystallinity, and as such. So how does amount of sample, it affects the curve? So in DTA analysis, the peak area of DTA curve is proportional to the mass of the sample. So this assumption is valid only over a certain range of amount of sample. In general, a few mg of powdered sample is always recommended for DTA measurements. So then comes the particle size. In DTA measurements, samples in the form of fine powders, they are generally preferred, except for polymers for which we have to use chopped fibers. Sample packing. The packing density of the sample, it influences the shape of the DTA curve. The tight packing influences the shape and interaction of the sample. Therefore, a reproducible method of packing sample is desirable. Heating rate. It has been observed that an increase in heating rate increases the procedural peak temperature, and sometimes it also increases the peak area. So mostly when we say heating rate, that is, it is either 10 degrees centigrade and 5 degrees centigrade per minute are performed. Then the atmosphere around the sample, similar to DTG, a flowing gas is preferable. That is mostly in an inert atmosphere. So here, a list of factors that influence the DTA curve has been shown here. Suppose first is the heating rate. So the effect is change in peak size and position. So what are the suggestion is that we always use a low heating rate in the range of 5 degrees centigrade to 10 degrees centigrade. Then location of the thermocouple, it produces irreproducible curve, so we should always standardize the thermocouple location. Atmosphere around the sample, it changes the curve, so we should always take inert gas. Then the amount of sample also hampers the peak size and position, so we should always take very minimum amount of sample. If for a particle size, it also produces irreproducible curves, so we should use very small uniform particle size. The particle packing density should always be standardized. We cannot take any sample container. It should always take a sample container so as to minimize the changes in the DTA peaks. Then coming to the sources of error. So there are a number of sources of error in DTA, and they can lead to difference in disturbances in the recordings. So first is the buoyancy effect. So if we take a thermally inert crucible, then there is a apparent mass change as the temperature increases. So why this is due to the effect of change in buoyancy of the gas in the sample environment with the temperature. However, in most modern instruments, this effect is negligible. So, but to avoid any ambiguity, we should always perform a blank run minus the sample and only with the crucible, so as to so as to avoid this buoyancy effect. So even condensation of the sample on the temperature sensor will affect the DTA curve. If there is fluctuation on the thermostats, there is a reaction between sample and container, the convection effect, the turbulence effect, the induction effect, all these will contribute to the errors in the DTA curves. Then coming to interpretation of DTA curves. So DTA curves of a pure compound, they represent the characteristic of that compound. So using DTA curve, one can correlate the changes in energy because of thermophysical and chemical change occurring in a compound because of heating the material. This can often provide us directly to the temperature at which the physicochemical transition are occurring. The change in DTA curve, it also gives us about the melting point, glass transition temperature, crystallization temperature. So to understand this, let us take the example of DTA curve of calcium oxalate in oxygen atmosphere, and the curve has been shown here in figure 11.5. This is for calcium oxalate dot H2O in oxygen atmosphere. This is a DTA curve. So here this curve indicates that DTA has three peaks. This is the first peak, which is endothermic in nature. This is the second peak, which is exothermic in nature, and this is the third peak, which is again endothermic in nature. So here this observation is also correlates with our data of the nature of the reaction. So we can also explain here by the chemistry of decomposition of calcium carbonate dot water when it is heated. So we know this is how we have studied. The first peak, it corresponds to the loss of water from the sample, thus it is endothermic in nature. In the second step, the calcium oxalate, it reacts with CaC2 forming calcium carbide plus CO2. Then in the third step, this calcium carbide, again it reforms calcium carbonate, sorry, this is calcium carbonate, it decomposes to form calcium oxide plus CO2. So, and this is theory, and this has been beautifully explained by the DTA curves. So DTA curves, they are both used qualitatively and quantitatively. Similar to TGA, the position and shapes of the peaks, they can be used to determine the composition of the sample. So as discussed here in equation 11.1, then they can also be used to relate to peak area, and how then we can also calculate the mass of the sample from the peak area. So similarly to the heat of the reaction can also be known. That is, using the calibration constant K, we can also calculate how the that is peak area is equal to, and the delta H we can also find out from the DTA curves. So this is the illustration. The figure 11.6 illustrates the determination of DTA peak curves. The difference in the initial and final base here, this is the initial and final base. The difference, it shows us the change in heat capacity. So the heat capacity, it can be calculated using this formula. Delta Hm is equal to delta Hr. This is the heat of the reaction. Mr means the molar mass of the compound, and small m is the mass of the substance that have been taken for analysis. So the heat capacity can be calculated as Cp is equal to K. K is the calibration constant, T2 minus T1 into M into H, where here capital H, it represents the rate of the heating, and K is the calibration factor. Then construction of phase diagram. The melting point can be recorded by DTA curve for a eutectic mixture of different sample with variable composition. These melting points, they can be used to construct a phase diagram. The critical temperature of organic compounds can be determined by also be DTA. Even the Curie temperature, Curie point temperature, can be determined by this by a DTA. So estimation of transition temperature. So the precise transition temperature, that is from melting point and boiling point, can be measured over a wide heating range. The temperature estimated for melting point, that is Tm, or boiling point, that is Tb, have been shown from the portion of the peak. Here it is shown in figure 11.7. In the first figure, a baseline meets the low and high temperature sides. Here this is the baseline which meets the low and high temperature sides and of the peak. So here then A is the intersection of the extrapolated baseline, and B is also the intersection of the inflection point. So here in exceptional case, so here the melting point Tm, it can be measured by using the sample which is closest to point C, and similarly the Tb can be measured. Then coming to the applications of DTA, the practical applications of DTA, how DTA is used. So first, it is used in qualitative and quantitative identification of minerals. So for the detection of many minerals in a sample, it is essential that it undergoes measurable energy changes in the temperature range used. Since most of the minerals, they undergo such changes, the choice of an appropriate temperature range should be a priority. So there are also other difficulties may arise. So oxidation of organic materials, it also masks the thermal effect of the substance. So organic materials, they have sometimes be removable by suitable solvent. So when clays or ores, they contain certain organic material, then a broad exothermic peak here, it occurs in the range of 200 to 600 degrees centigrade. So whenever we see a broad exothermic peak in this region, it indicates that an organic material is present in the sample. So however, there are very difficulties when we for the identification of such type of samples. So here an example has been given. Kaolinite and illite are present in the same sample, almost completely overlapping. So here for these are the DTA curves for three types of clays, that is kaolinite, montmorillonite and illite. And you see the for kaolinite and illite, almost similar type of DTA curves it has been shown. So if representative DTA curve it has been shown here, it may be observed that none of these have shown an exothermic peak in the range of 200 to 600 degrees centigrade as we have talked, but there has been no mention, no presence of 200 to 600 degrees centigrade. So this is how, so DTA curves will help in identification of different types of clays. Then DTA curves is also used for analysis of different types of organic, like polymeric materials. So it provides important certain parameters like the TG, that is the glass transition temperature, TM, that is the melting temperature, the TC, crystallization temperature, and the TD, that is the decomposition temperature of a particular polymer. So the here the DTA technique is also used for analyzing a polymeric mixture qualitatively and quantitatively. So here 11.9 you can see the different thermal curve of 7 components of polymeric mixture. So here 11.10 you can see the endothermic and exothermic peak of different polymers. So it shows the characteristics of all the polymers, and from these polymers, comparing this data, we see that PTFE for 51% of ethylene and 49% of propylene present in the analyzed block copolymer. So looking at this data in these two, so here looking at this data we can find out the amount of polymer that is present in the a particular polymeric mixture. So another important that is known from DTA is the glass transition temperature, that is TG. So here glass transition temperature means it is the transition from the chains of the polymer to a glassy state. The first evidence was for DTA was provided by a transition at around 28 degrees centigrade. So at such transition, so it is not associated with a sudden change, but we have this relation, that is TG by TM is equal to 0.66. So the glass transition of a temperature, it can be obtained using number molecular average of the polymer TG to be this, and then we can calculate the TG value. Then from the DTA curve, we can also measure the crystallinity. So which is given as delta H by delta HF star. So delta HF star is the theoretical value and delta HF is the measured value. So the crystallinity, this is the mass fraction crystallinity, that is chi. It can be calculated as delta H minus delta HF by delta HC. So here A is for our sample and here delta HF for C means the theoretical calculate for the perfect crystalline material. Then degree of polymerization can also be calculated from the area of the DTA curve. So if we consider the DTA curve, then calculating the area under the peak, we can calculate the degree of polymerization of the particular sample. So DTA has also been used in the analysis of biological materials. So what are the biological materials? So it has been used for a multi-component molecular non-homogeneous materials, biological systems present even in uh, static state. They have also shown meaningful results in DTA. For fresh biological material, they consist of materials of active body of plants and animals. So DTA has been curves of 4 leaf samples. They have been found out the amount of oxygen that is taken up by different amount of leaf samples. Then DTA of plant materials have also been performed, and they to know their decomposition and oxidation effects. Similarly, DTA has also been used for high energy materials, explosives, cements, pharmaceuticals, etc. So then coming to DSC. DSC is yet another principle which is similar to in another instrument similar to that of DTA. So a DTA DSC curve, it consists of x-axis is temperature and y-axis is flow rate, that is the heat flow rate. Then the typical instrumentation of a DSC, it has been shown here in figure 11.12a, and the different types of heating arrangements has been shown in figure 11.12b. So this is a particular DSC curve that has been shown here. The peak area is similarly calculated as plus minus delta hm into k, where k is the calibration constant. So here, unlike DTA, it is independent of temperature. So using equation 11.6, we can also calculate delta H and the enthalpy change, it can be calculated. Also we can calculate the Cp, that is using the formula. So using this formula, and similarly this is how DSC is interpreted. The factors affecting DSC, these are also, we have the different instrumental factor and sample characteristics. The sources of error are similar to that of that has been studied for TG and DTA. Then interpretation of DSC curves. So DSC curve of a pure compound is a fingerprint of that compound because the transition temperature and the heat required for the transition are particular for a particular temperature. So here 11.14, it shows the change in behavior of a polymeric materials in DSC. How does a polymeric material, it behaves like, if we keep on increasing the temperature, first it is hard brittle in nature, then it becomes a plastic, flexible, then deformable, then viscous, then labile flow, and then ultimately it undergoes deterioration. So this, in this way, DSC technique is helpful in understanding the different type of transitions that occur within the polymeric substance. So the heat of the reaction, that is delta HR, it can also be calculated using the following equation. So DSC is particularly useful because it measures the energy changes, heat energy change as a function of temperature. So we can know, using this we can know the crystallization temperature of a polymeric material, the glass transition temperature, the degradation temperature, and all other temperatures of our material under analysis. DSC curves may also be used to evaluate the purity of a drug and polymer. We also know that drug polymer interaction is very important, so that is also measured by DSC. Then waxes and fats in pharmaceutical industry, they are also characterized by DSC. So DSC has many that applications, practical life applications. So some of the advantages of DSC is that it is a very simple and rapid procedure. It is very ideal for comparison of sample purity. In quality control, it does not require high temperature, does not require calibration, and the use of melting. Here it occurs rather than a freezing curve. It avoids the problem which is associated with the supercooling of the sample and instability of the melt and other factors. So this is a very reliable and easy method. So next is thermometric titrations. So thermometric titrations means they are similar to that of thermogravimetry. So these are the titrations that are formed, and here the we here with the addition of titrant, we plot a temperature versus the volume of the titrant. So this is called as enthalpy titration, and the curve are called as enthalpograms. So here a particular enthalpogram for exothermic reaction and endothermic reaction, it has been shown here in figure 11.16. So this is how does the, this is the curve representing an enthalpogram or thermometric titration, that is abbreviated as TT. So this is the setup schematic layout for thermometric titration assembly and the bridge circuit. So this is an efficient adiabatic cell for thermometric titrations. It consists of a delivery pump, an adiabatic cell, a calibration unit, and a temperature sensing system. And finally, ultimately, the amplifier and the recorder. So this is the application of thermometric titrations. They have been widely used to understand all types of titration, including neutralization reactions, redox reactions, precipitation reactions. So table 11.2, it shows the summary of application of thermometric titrations. It has been used for all fundamental analytical titrations, and the information that we can obtain is delta HR, that is the heat of the reaction, free energy, entropy, stoichiometry, and the concentration of the unknown. So this is an example of figure 11.2 to 20. You can see the comparison of potentiometric and thermometric titrations for HCl and H3BO3 with NaOH. So this is the A represents the potentiometric titration curve and B represents the thermometric titrations curve. So thermometric titrations curves are, they are more specific and they are more sensitive. This in figure 11.21, you can see the thermometric titration curve for Ca2 plus and Ng2 plus with ETTA. So these are some of the examples by which you can calculate the stability constant from thermometric titrations. So this is all about DTA, DSC and thermometric titrations. So with this, we'll finish this chapter. In next class, we'll study another part.